everyone. This is our second colloquium for the semester. And today we have Camilo Montoya, our graduate student here in FIU, who wants to present on complex variables. He'll be going over characterization of analytic functions, meromorphic functions, residue theorem, basic things from complex variables. And here he is.
If we get to it. Thank you guys. So we are considering what? I'm recording it on my thing. Couldn't come on.
But that's because that's a better side.
Yeah, it is my better. Okay, so we're considering functions of a complex variable z. So let z be a complex number, right? We express z as x plus I, y. The complex number ends up, I'm going to breeze through this stuff, guys. The complex numbers end up forming a plane. So for any point z here, he has his x coordinate, his iy coordinate, and we say z is x plus iy. There's the conjugate of z. You just negate the imaginary part, so here's negative iy. And this one here is z bar. So z bar is x minus iy. And we have these relations. X, which is the real part of z, is z plus z bar over 2. Y, which is the imaginary part of z, is z minus z bar over 2y. So back in multivariable calculus, we considered functions from R2 to R, or R2 to R2. So in this class, in this colloquium, we're interested in a subset of these functions. So the complex plane, it's a plane. This is we identify it with R2, right? And we're considering C to the C. We're considering a proper subset of this. These are all the functions from C to C, right? So we're considering a subset of functions, all the f's, such that, well, f's from R2 to R2, but we're going to identify them with C. I'm sorry, guys. I'm sick as hell. Okay. Of these functions, we're interested in a subset of them, a proper subset actually, which are the f's that are what we call analytic in Z, analytic in Z, in a complex variable. What that means now, I'll get to it. It just means that f is a direct function of z. It doesn't have nothing to do with z bar. We're interested in direct or analytic, or explicit functions of z of a complex variable. For example, the function let f of z. Well, actually, so first we're gonna identify every function with its image, but just consider f of x comma y, function of two variables. Consider this guy, x squared minus y squared plus 2xyi. This is a direct function of a complex variable z. We just this is nothing more than x plus iy squared, which we identify to z squared. And this is f of z. On the other hand, for example, a function like g of xy. Those x squared plus y squared minus 2xyi. This is not a function that's expressible as a direct function of z. This is just a random function of two variables. But it's not a direct function of z. So we're interested in guys like this. So now, once we have these analytic functions in Z. They're expressible as a function in x plus iy. We want to do stuff with them, like differentiate them and stuff. So that, like I told you guys in the complex class, I'm going to be proving a sequence of if and only ifs that characterize holomorphic functions in every possible, like I mean, in all the different ways. So that really, it's a bunch of if and only ifs so that we can start anywhere. We can take our definition to be any of these, and they're equivalent to all the other ones. So for now, we're going to take our definition to be, I guess, the one you guys use in class. So definition, F is analytic or holomorphic. So F from U, so F is a function from U, a subset of complex plane, to the complex plane. We say this function is analytic or holomorphic if it's complex differentiable for every Z and U, F prime of Z or F dz, whatever, and this is defined to be the limit at Z equal at every Z0 in U, in the domain. This quotient here exists and is unique, and it's independent of the manner in which we approach Z0. I'll explain that right now. Z minus F of Z0. And this is the same thing as limit as H goes to 0 of F of. These things are the same thing. So now, a function is holomorphic if the manner in which we approach Z0 is independent of the path we choose. Meaning, here's Z0, and we can approach Z0 from here, from here, from here, from here, any possible direction we want. In particular, we can approach it via what we're going to identify with the partial derivatives of x and y. Meaning, like, we approach from like this direction, this is a partial with respect to x, right? And we approach in this direction is a partial with respect to y. So from here is, the Cauchy-Riemann equations are just going to spit out, for example, so we need this thing to exist regardless of the manner in which we approach Z0. So for example, and they need to be equal so that this limit, the limit, for example, as h goes to 0, but h is real, meaning we're approaching it, h is a real number, of this thing, f of z plus h minus f of z over h. Well, actually, under the identification of x as f of z as a function of x and y, really, where only the h is real, so that we're only affecting the x component. So this is like saying f of x plus h y minus f of x y limit over h, and this is nothing more than the partial of f with respect to x.
Remember, you're recording over here, so show.
Yeah. And similarly, the limit as h goes to 0, but where h is still real, but now we're going to multiply that real number by imaginary component. So we're going to do f of z plus ih minus f of z over h. This is nothing more than the limit, same thing, of f of x comma y plus h, x, y, over h. And this is nothing more than the partial of f with respect to y. Well, actually, over iy. No, I have a I here, so I don't have an I there. Factored it out. Yeah, over iy. And so that this is nothing, you factor out the I, this is nothing more than 1 over I as a partial with respect to y. And remember what I said, a function is holomorphic if the manner in which we approach z0 or the manner in which h goes to 0, these things are independent. It doesn't matter which way I approach it, so that these things have to be equal. In other words, partial f, partial y has to be I times partial f, partial x. And these are the celebrated Cauchy-Riemann equations. They're writing right now in the form that you guys know. So, for example, if we now we're going to identify f from u to c with its image, so that we can express f of z is really just f of x comma y as u of x comma y plus I times b x comma y. Or shorthand, just u plus iv, where u and v are functions from R2 to R. u, v, functions from R2 to R. And if this is the case, then we have to have that the partial with respect to y of u of f, u plus iv, is I times the partial with respect to x of u plus iv. And so this is partial u, partial y, plus I, partial v, partial y, has to be I times partial u, partial x, minus I times I is negative 1, so minus v partial x. And just saying, alright, well, if these things have to be equal, then the real part of this side has to be equal to the real part of that side, the imaginary part of this side. So this is the imaginary part of this one, this is the imaginary part of that one. This is the real part of this side, this is the real part of this side. So that we just get this, the system of two partial differential equations, which are the Cauchy-Riemann equations. We have that, the real part of this is that, so we have, let's just do a little subscript notation. So we have uy minus is equal to negative bx, and we have vy is equal to ux. You guys know this notation, right? The partial. This just means a partial of u with respect to x, partial t with respect to y. Similarly, like this guy could be called fy is I of x. And so if you identify the function with its image in the complex plane, you get the Cauchy-Riemann equation. So you see how all I did was take this derivative, and it has to be independent of the path I choose. If I take it just purely vertical path, I'll get the partial with respect to y. And a purely horizontal path, I'll get the partial with respect to x. The definition, though, is this has to hold for any path I take, so in particular, these two have to be equal. This limit and this limit have to be equal, and they have to be unique and equal, so that's the Cauchy-Riemann equation. So now the main part of this lecture today.
Why does uy have to equal negative ux?
And I have a negative here.
Okay.
When I multiply this into here, so I'm taking a partial of this, so I take the partial of each one. But there's I here. I times I is negative 1.
No, I understand, but why wouldn't it be u sub y equals u sub x?
U sub y, what? Where? What?
Why wouldn't it be u sub y equals u sub x? Yeah, exactly. Because you're getting them from the partials are equal, right?
Yeah, the real part of this side and the real part of that side have to be equal. Imagine this.
Okay.
So
okay.
this is the real part of this side.
Okay.
This is the, anything with the factored out
Yeah.
I is the imaginary part. So this is the imaginary part. But in this one, once I multiply all this in, this is the imaginary part and this is the real part with the negatives.
I get it.
So the following are equivalent. F is holomorphic on U. Remember, I took my definition to be complex. F is holomorphic if it's complex differentiable. This is complex differentiable. At every point in its domain. So the following are equivalent. Meaning, I could have picked any of these to be my definition and I'll just prove it's equivalent to the rest. I actually, for example, I just did the second part. I proved that 1 implies 2. F satisfies the Cauchy-Riemann equations, which are these guys right here. And as you see it, if F is complex differentiable, it has to satisfy Fy is I of x. But if that's the case, it's equivalent to the Cauchy-Riemann equation. 3 is the partial F, partial Z bar is 0, which is, I'll show you guys that one, that's just a restatement of Cauchy-Riemann equation. Then now the interesting stuff, which you guys are going to see in which, when I saw it, like, I understood the stuff that was going on in class, but I didn't know how it all connected together, and that's what I'm attempting to do here, is connect it all together. This guy, I'm going to explain what these guys mean. If you integrate the holomorphic function over some, so I'll talk about line integrals in a little bit. The integral over any closed C1 curve, or piecewise continuously differentiable curve, is 0. And 5 is a locally expandable as a power series in Z. Meaning it has a power series. So, for example, right now we'll show that 1 implies 2, which is this right here. We'll show that. Actually, we'll show it's 1 if and only if 2, if and only if 3. This is almost trivial. If you want, so I already did. I can reverse all the arrows here, and that shows that 1 if and only if 2. I gotta show if and only if 3, and like I said, this thing. So f is a function of x and y, right? We have its partials. We have fx and fy. We're gonna define the partial of f with respect to z and z bar. With respect to z, this is gonna be 1/2 partial. With respect to x, the z is minus I partial with respect to y. And then the partial of f with respect to z bar is going to be 1/2 partial f partial x plus I partial f partial y. And so I'm just defining operators here. I'm saying take the partials, multiply it by I, sum them up, divide by 2 is just an operator. So part 3 says that the partial with respect to z bar is 0. This is just encoding the Cauchy-Riemann equations in an elegant manner. In fact, in most textbooks, they take this to be the definition. This is the simplest one. It's the most compact one. And this, well, you'll see the theorem. All of these are the same thing. So that I can start. I started with here, and I started this, whatever. I could have started here and showed the rest. I could have started here and showed the rest. So for 3, to show, for example, 2 if and only if 3. If f satisfies the Cauchy-Riemann equations, then we have this. We have that. So f is u plus iv, and our operator with respect to z bar is 1/2. So partial with respect to f. I don't want to put this. So we just multiply this out. This is 1/2 partial x plus And what do we get? This is just. Okay, so basically, eventually what we'll get here. Well, I'll multiply everything out, group all the like terms basically, and I'll just get. Here I'll get uy. So dot dot dot. I'll get uy plus vx plus I times ux minus vy. Once I multiply all this out, and this is, if I'm assuming that 2 and trying to show 3, actually if and only if, this is 0 plus 0i. If f satisfies the Cauchy-Riemann equation. So that, this is just another way, saying that the complex differentiable, or saying that holomorphic function doesn't depend on z bar, is just another way of saying it satisfies the Cauchy-Riemann equation. Is a big 0 is a big 0. If this holds. So those are just nice ways, because you might see them in later on in books. But now I'll really get to the cool stuff. But like trying to explain kind of what some of this stuff means. So actually we have to take a detour into line angles.
You mind if I take a couple pictures?
Sorry?
You mind if I take a couple pictures?
He doesn't have a choice, you have to take it.
You can just take them right now. You don't have to ask them.
So for example, we have, suppose this is our domain U in which f is defined on. If we have a curve inside of U, call this guy gamma. Well, this is a closed, no, let's just keep it arbitrary for the moment. So let me just remind you guys what curves are. A curve gamma is it's one of these guys, but you parameterize it with one dimension. So gamma is a function from A to B into U, subset of C. That maps, for example, phi of A. Gamma of A is Z0, gamma of B is the second endpoint, and the in between just kind of scrolls through the thing. And so if we have a parameterization of gamma, so that, for example, gamma of t is gamma 1 of t plus I gamma 2 of t. We parameterize it. And if this guy is continuously differentiable. You guys know what continuously differentiable is? Okay. So the curve is said to be, so gamma is C1 of AB. That means it's continuously differentiable on AB. If gamma is continuous, gamma is continuous on AB. Gamma prime exists on AB, open. It's differentiable everywhere inside the thing. And 3, we can extend it to the whole thing. We can extend gamma prime to all of AB. And this just means that the limit as for example, as t goes to A minus of gamma prime of t is gamma prime of A. The other one, the limit, we can extend it as t goes to B. I got it back. B minus. This is A plus. Of gamma prime of t is gamma prime of B. So a curve is called continuous differentiable these three things hold. And that's called C1. So this is 1 times continuously differentiable. You can talk about CK, which is a curve is CK if it's K times continuously differentiable. So this holds for the first K minus 1 derivatives, and on the Kth derivative, these you can extend it continuously to the endpoints. So that's a continuously differentiable curve. So now if we have gamma, a curve from whatever AB to U, and then let's say F is continuously differentiable on U. It's C1 of U on U. Then you can define, then we just define the line integral. And I'm going to need this later, so I'm doing it. We're going to define the line integral, the integral over gamma of f of z dz. This is going to be the integral from a to b of f of gamma of t times gamma prime of t dt. And line integrals have these this really cool, really elementary estimate, for example. And this is called the ML formula. The ML formula for line integrals. The integral around any curve of f of z dz, absolute value of him, is less than or equal to ml, where m is a bound on f. Bound on f on the curve along gamma, and L is the length of the curve. It's called the ML formula. It's actually really easy to prove. It's just that whatever this integral is, as defined here, is less than or equal to you maximize. So it's like this. It's like analogous to one-dimensional integrals. Suppose you have a function like that. You have a and b here, and right, the integral is this area from a to b. Well, that integral is going to be less than. Let's say the max on a to b is here at b. The integral is going to be less than if I maximize the function the whole time and multiply by the length of the curve. So that I'm saying this area is less than or equal to this area. But I'll need that too, the ML formula. Okay, so that was our quick detour into path integrals, and now we can start on the cool stuff, like proving that 1 is the same thing as 4. Let me show you what this means. So now this is where things get cool, and this is where I'm going to start explaining stuff. So now we want to show 1 if and only if 4. One direction, so the first direction, is what's known as Cauchy's theorem. Cauchy's integral theorem. And let me just write it now. The other direction is what's known as Morera's theorem. These are important theorems that you'll learn in class, and when I learned them, like, I understood them and all that stuff, but I just, like, I don't know, I didn't connect it all, you know? Now I could, you know, now I do, but, so we'll show both of them. So for Cauchy's theorem, so we want to show that if f is holomorphic, it implies that the integral around any closed curve, so actually here, gamma is a closed C1 curve. And actually we can make it piecewise. We can just, that just means glue a bunch of C1 curves along the endpoints, and it'll be piecewise. And the theorem will still be true.
So they at those endpoints, they wouldn't have to be continuous and differentiable?
Of course. The derivative.
No, like you said, piecewise. So each one is just a curve, and with those endpoints have to be for this to happen.
If it has to be differentiable at the endpoints?
Yeah, you said it was piecewise, so
Yeah, I guess no.
it doesn't have to be?
No, I can do that. I can do this. Do a piece like that, and another piece like that,
Okay.
another piece like that, and just close it. I'm saying if I integrate f along some curve like this will be piecewise, it'll still be 0.
So you just need it to be continuous?
No, I need it to be continuously differentiable.
No, at the endpoints. Just continuous at the endpoints. Because it looks like you're starting and ending,
So,
but you
no,
might
curve
have
has to
something
be
that's not
C1.
differentiable.
That means that it's continuous on AB.
I know, but you were saying this doesn't even have to be continuously differentiable. You said that this could be piecewise.
Piecewise continuously differentiable. So
Okay.
it just means on the pieces, there's all the different pieces are C1.
But what I'm saying is look at the,
And the endpoints have to match. Like,
they have to match, but they don't have to be differentiable at the endpoints.
no.
Okay.
No. It just has to be, they just have to match, yeah, so it just has to be continuous at the endpoints if you make it piecewise.
Yeah.
So, we're proving Cauchy's theorem. Okay, so there's two ways to do this. One is to show that f has a, what they call a primitive antiderivative. So f has, they call a primitive antiderivative, which actually I'm going to show that every f has a primitive antiderivative for the other direction. But I can actually show it now and also use it here, antiderivative. And that just means that there exists holomorphic function capital F such that the derivative of capital F is little f. Or we can just use, remember, 1 implies 4, this is a line integral on a plane. So that we can just use Calc 3 too. We can use Green's theorem from Calc 3. So that Green's theorem said, Green's theorem relates, so again we have some curve. So this is inside, the inside is the domain D. The outside is the boundary of the domain D. The actual curve is the boundary of the domain. And Green's theorem says that the integral around the boundary of the domain of some expression like m dx plus n dy, this can be related to the double integral around the domain of some special partials, which I already forgot. It's mx minus ny. So now, if we use this, it follows really quickly, because actually, you just compute the imaginary, the real and imaginary parts separately, and the Cauchy-Riemann equations will just pop out. Like, I can do it if you guys want. But then I gotta go into differential forms.
Camilo, are you sure it's not MYNX? I may be confused.
Yeah, you're right. It's my and x, yeah. But in a second, I mean, oh, I gotta erase this. Screw it, let's do it. So we're integral around the boundary of the domain of, so we're trying to prove that the integral around f, if f is analytic, meaning if it satisfies the Cauchy-Riemann equations, then the integral around a closed curve, so this little circle thing means it's closed, of f of z dz, we're trying to prove this is 0. Well, f is, this is the integral around the curve, f is u plus iv. And dz is nothing but it's dx plus I dy. when you multiply all this out and integrate the imaginary and real parts separately, this is integral. This is u dx minus plus ui dy plus iv dx minus v dy. And we collect in terms of real and imaginary parts. So the real part is here. This is u dx minus v dy plus I times u dy plus v dx. And now we apply Green's theorem to each of these pieces individually. By Green's theorem, this is the double integral around, so here gamma is the boundary of the domain. So that this becomes a double integral over the domain of these partials. So this is going to be, in here we're going to get uy minus dx dy plus I times double integral over the domain, and here we'll get ux minus dy dx dy. And if f is holomorphic, it means that this is equal to 0 and this is equal to 0. If f satisfies the Cauchy-Riemann equation, right? So this is a big 0 plus 0. So that this direction is proved, let me actually write it over here. And I'm going to explain, the next one is where you'll see what this actually means. So I just showed, so f hollow implies that the integral around any closed C1 curve is 0. As you can see, if f is holomorphic, it satisfies the Cauchy-Riemann equations, and they just show up right there, and the integral is 0. So now we want to prove the other direction. And that's what's known as Cauchy's theorem. Cauchy, it was a big theorem. It was showing, it was an important thing, and you'll see why. Because you'll see that the integral around any closed curve being 0, it means that that complex, when you integrate when you integrate holomorphic functions around any curve, the actual curve, the actual path that you take from Z0 to Z1 doesn't matter. The only thing that matters are the endpoints. Okay, you'll see what that means now. We're going to do the other direction, which was Moreira's theorem.
So you're missing a factor of the derivative of the path over here, right?
What?
Over here, when you changed it from line integral to double integral?
Where?
You have to multiply by the derivative of the path, right?
No, I didn't substitute a parametrization. That's only when I substitute in a parametrization. But yeah, like, so if you have that gamma, then the integral of f dz, and you plug in z equals gamma of t, and yeah, this becomes the integral f of gamma of t, f of z, times dz. But dz is gamma prime of t dt. So then when you explicitly substitute a parametrization, then yeah, you get. But here, I didn't do no substitute. I just multiplied this out like differential forms.
Okay.
And the Cauchy-Riemann equation just fell out. So now, like I was saying about these homomorphic functions, they're really special because, all right, remember when we differentiate them at a point, the path that we take as we go to that point doesn't matter. And when we integrate them along a path, the path along which we're integrating also doesn't matter. The only thing that matters are the endpoints, and you'll see it right now. So now we're proving Moreira's theorem. We're going to prove this direction. if the integral is around, if the integral of f around any closed curve is 0, then it's holomorphic. This is what we want to prove. And this was actually it's a partial result. It's a partial reverse. We actually also have to assume continuity. So also assume f is continuous. So it's actually only a partial converse. Alright, and we do it as such. This is so we're assuming this, showing this. So now, this is what I mean. So for example, take, we have two, let gamma 1, let gamma and tau, let gamma and tau be paths from z0 to z1. So that, for example, here's z0, here's z1. This is gamma, and this is tau. There are two paths from z0 to z1. If the integral around any closed curve, this is my assumption, if the integral around any closed curve is 0, then we can concatenate paths, meaning I can go from z0 to z1 along gamma, and then do the inverse of tau to go right back to z0. Just do tau, but in reverse. So that I define the path gamma plus tau inverse. This will be a path from z0 to z0. In other words, closed. It's a closed path, so that we have that the integral around gamma plus tau inverse of f of z dz is 0. But it's 0, but actually we'll decompose this as the integral along gamma of f of z dz plus the integral along tau inverse. And now if you remember, which is probably something I forgot to mention, it's the integral along any curve, if you do it's the negative of going the opposite, the other way. Meaning, this is just the integral along gamma plus minus the integral along tau. And by assumption, if this is 0, that implies that the integral along gamma, f of z dz, is the integral along tau, f of z dz. And you see what this means now. This literally means that if you integrate holomorphic functions along any path, it's independent of the path. The only thing that matters are the endpoints. Because if the integral around it is 0, then you just do this, and I just showed that even if gamma and tau are different paths, the integrals are equal. See that? So that's what it means. You know, at first, when I first learned this, I was like, yeah, cool, the integral is 0. You know, what does that tell me? I don't know. Now I understand what it means. It means the homomorphic functions are independent of the path, the actual path. They only matter on the endpoints.
You have like 10 minutes.
What?
You have like 10 minutes.
Forget about it. Jesus Christ. Okay. So actually, the medicine is kicking in a little bit. I feel a little better somehow. So that I'll keep going if you guys are down. Yeah. What do we have? What are we trying to do? Okay, so we're proving Morera's theorem now. We're trying to prove that the integral around a closed curve 0 implies it's holomorphic. Well, we just defined this guy, it's the primitive antiderivative. Define f of z, so let z0 be in U, and define f of z as the integral from z0 to z of f of z. All we need to do, we're going to show that this f is actually, that this f is differentiable. We're going to show that it's got a complex derivative. So how do we do that? Well, we calculate the difference quotient. F of z plus h minus f of z over h. Actually, I'm going to just do it all at once. The absolute value of this, I'm trying to show that f prime is at little f. So this minus f of z, I'm going to show this is bounded, and it's actually bounded by 0. It goes to 0. So this is the integral from z0 to z. Oh, this is f of zeta, bro. You guys gotta catch this. I can't put the same variable in there. So 1 over h times this guy, and now, well, this is z plus h. This is from z0 to z of f of zeta d zeta minus f of z. And so now we combine these two. Here the path is going to be the horizontal from, we're going to go horizontally from z0 to z, and then from z to z plus h. So just like Calc 1 integrals, this is going to cancel out and just leave 1 over h, the integral from z to z plus h, right? And I'm doing z0 to z, and then adding a little vector h somewhere around there. But I'm taking the whole z0 to z off, so it's just z to h. And this is less than or equal to 1 over the absolute value of h times the integral times this integral. Z to z plus h. And now, we're assuming, remember we assumed f is continuous, right? F is continuous, that implies that the absolute value of f of zeta minus f of z is less than epsilon whenever zeta minus z is less than some delta. Well, we're gonna put as, so zeta's here. Zeta's in the path that we're integrating. And so the zeta is actually on the path from z to z plus h. So here's z. This is the vector h, so that here is z plus h. And zeta is actually a point on the path that we're integrating. D zeta. Zeta's on there. So that as h goes to 0, zeta goes to z. You guys see that? Again, zeta is on the path from z to z plus h. So that as h goes to 0, zeta has to go to z. There's no other way to say that. So that this is the absolute value of h. Again, so now, basically I'm going to take the limit as h goes to 0. As h goes to 0 of this, I'll have this here goes to f of zeta goes to f of z. So wait, I bounded that. This is less than or equal to half the integral from z to z plus h f of zeta and f of z. Zeta. And now this in here is epsilon. We're using the bound, the continuity of f. So this is actually 1 over absolute value of h. We're going to factor out epsilon, and we're just going to get the integral from z to z plus h of 1 d zeta. and now the limit as h goes to 0.